Signal processing, as the name implies, concerns the processing of signals. These signals might be audio signals, such as the one you're listening to now. They could be image or video signals, such as the one you're watching now. Or they could be data signals, such as transmitted between devices. USB is an example of how different devices can communicate together. What might we want to do with audio signals?
Well, we can add sound effects.
We can correct for room acoustics via equalization, and we can remove noise from the signal. For example, audio equipment often picks up the 50 Hz hum from power lines, and it's relatively easy to build a notch filter to remove 50 Hz and the higher order harmonics. With images, we can improve the contrast of photographs. This requires scanning the photograph for edges, which can be done using a high-pass filter, for example, and then applying various effects to increase the contrast in those regions. In communications, we need to take the original analog or digital signal, we need to modulate it, send it somehow. At the receiving end, we then need to demodulate it and decode it. If we are transmitting digital signals, then we need to work out how to represent each digital message, and that involves pulse shaping. How do we choose the pulse in such a way as to try to minimize the amount of bandwidth used while making sure that the receiver can still receive the signal to the desired level of accuracy? Data analysis is another application of signal processing where you can try to find hidden meaning in data. In particular, one of the earliest applications was looking for periodicity in sunspot data. Basic frequency domain techniques allow us to work out whether there are hidden periodicities in a signal or not. Another standard application of signal processing is changing sampling rates. Audio might have been sampled at 48 kHz, but then needs to be upsampled to 96 kHz to be compatible with the rest of the system. A high-resolution photograph that you've taken might need to be downsampled before displayed on a web page. These upsampling and downsampling techniques are directly relevant to what we're going to be talking about today, which involves sampling of signals, going from a continuous time signal to a discrete time signal. Before getting to that though, let's look to see what it means to go from an analog signal to a digital signal, and how we might then process that signal in the digital domain, and then how we might convert it back to the analog domain. Going to our magic whiteboard, we can draw the fundamental building block. We have our analog signal coming in here, which we denote by x of t. It gets converted to a digital signal by putting it through an analog-to-digital converter. This will require sampling. Normally that's done uniformly in time. So our signal, x of t, is converted to one x of k, where k is now an integer. In more advanced courses, you'd worry about the resolution or the quantization with which this is done. But for now, we just assume that x of k is a perfect replica of x of t, it's just we have sampled it once per unit of time. We are now in the digital domain, and therefore we can apply our digital signal processing techniques to our signal x of k to produce a signal y of k. Once we have finished processing our data in the digital domain, we can then put y of k through a digital to analog converter to convert it back to a continuous time signal. And so in this way, we have constructed a signal processing module that takes an analog signal x of t and produces an analog signal y of t. But the key part of it, where we have our most flexibility, is with the digital signal processing right in the middle. Now, of course, we rely on other clever people to design A to D converters and D to A converters that do their job well. But our job as a digital signal processing engineer is to design this middle block, to process the signal x of k to produce y of k in such a way that the overall transfer from x of t to y of t is what's required. Now, why don't we simply process everything in the time domain? Well, in the olden days, people would do that, and a basic filter would look like the signal comes in and we put it through a resistor and capacitor, for example, for a very primitive low-pass filter. There are many disadvantages of this though. Firstly, you are quite limited in what you can do. You can design filters. Their design is somewhat complicated because if you add a second low-pass filter in front of this first one, then the impedance of each of these low-pass filters affects the other. Whereas in the digital domain, we'll find out later that if we put two filters, one after the other, then there is no interference between the two filters and they function the same as if they were on their own, so to speak. Given a system such as this, there are two basic questions. The first basic question is, how do we understand what these three inside blocks do to our continuous time signal? Once we understand what these three blocks can do to our signal path from xt to y of t, the next question is, how can we design our DSP block in here to achieve a particular function, a particular transformation from the input to the output? An example would be the input x of t coming from a microphone. The output y of t is what I want to record to video. I would like to process the output of my microphone to try to improve how it sounds. I can try to remove noise, and I can try to correct for any room reverberation, for example. Before answering such questions, it's natural to ask, well, what sorts of things can we do in this DSP block here? What sorts of operations are normal to be done in here? A DSP block takes a discrete time signal, x of k, processes it in some way that we're about to talk about, and produces another discrete time signal, y of k. K is an integer, and x of k and y of k can take on real or complex values. One of the simplest forms that this DSP function can take is y of k is equal to some sort of a weighted average of x of k and some of its neighbours. For example, I could set y of k to be equal to x of k plus a half of x of k minus 1. We can see that this gives us a rule for how to find the output at any time k. If I want to know the output at time 5, well, according to my rule, I just look to find out what the input is at time 5, look to see what the input is at time 4, and do half times the input at time 4 plus the input at time 5, and that gives me the output at time 5. This rule is what's known as a moving average filter or a finite impulse response filter. We are going to be talking about impulse responses a bit later. Another simple rule is of a very similar form. I can have y of k is equal to x of k plus, and now I can add on some of not a previous value of x, but a previous value of y. And this forms what's known as an autoregressive filter, in statistical terms anyway, or as an infinite impulse response filter. Again, we'll be talking about impulse responses presently. Of course, we can combine these two systems, and so in general, I like to talk about autoregressive moving average filters when you combine these two together. So in other words, for this particular filter here, I can add on a quarter times x of k minus 2, for example. Now, technically speaking, you talk about ARMA filters when you look at statistical signal processing. However, I'm used to that terminology, so I will use it here as well. To remind ourselves where we are, we have in the real world a continuous time input signal x of t that goes through an analog-to-digital converter. It gets fed into our DSP block, which we now know can implement an ARMA filter, among other things, and the output then goes to a digital-to-analog converter before being sent to the outside world as a continuous time signal. And we want to understand what is the effect of choosing our DSP block to be, for example, an ARMA filter on the overall signal path from xt to y of t. And furthermore, if I wanted to apply a bandpass filter to my signal from x of t to y of t, how would I choose my ARMA system to achieve that? It turns out to understand this particular system that I have drawn here with an ARMA filter in here, it suffices to work in what's known as the frequency domain. Humans have an intuitive understanding of frequency. We can listen to sounds and say this is a low frequency sound, that's a high frequency sound. And it's important to always keep in mind that our intuition about what frequency is really is what frequency is about. In fact, we will be introducing the Fourier Transform soon, and our ears actually do perform some kind of a Fourier Transform. The audio waves come in, and our ear, its geometric structure, somehow separates the sound into its different frequency components. And so our brain literally does hear sounds coming in at different frequencies. It's essentially doing a Fourier transform on the incoming signal. So there is something very fundamental about frequency. And we can ask what it is, and in fact we can give a very good answer why frequency is so special. It's worth keeping in mind that we actually have two different types of systems to look at. From x of t to y of t, we have a continuous time system, whereas from the input of our DSP to the output of our DSP block, we have a discrete time system. For both systems, for both the continuous time system and the discrete time system, we are able to define what it means for a signal to be oscillating at a certain frequency. And moreover, given an arbitrary signal, we can decompose that signal into its different frequency components. It's important to keep in mind that even though the mathematics might look a bit different between continuous time systems and discrete time systems, there is just one single concept of frequency. It's the same thing. A frequency in the discrete time domain is the same thing as a frequency in the continuous time domain. It takes a little bit of getting used to how to manipulate the mathematics so this comes out correctly, but the key point is frequency is the same concept whether we're in discrete time or continuous time. We already gave one example before of frequency, and that's our hearing. Not just our hearing, but other mechanical systems seem to have frequency responses, or in particular, we might notice that certain objects tend to resonate at certain frequencies. The annoying rattle in your car tends to have a particular frequency. The sound of the rattle does not change from day to day. It essentially stays at the same frequency no matter what the excitation is that caused the rattle in the first place. Now, it may sound like frequency is very special on its own, but that's not actually true. Remember the examples I gave were hearing and your car? Well, these are special types of systems in that they satisfy a very special property, or they approximately satisfy it. And this property is known as linear time invariance. In fact, there are two properties, linearity and time invariance. We can talk about continuous time LTI systems and discrete time LTI systems, where LTI, of course, stands for linear time invariant. Our continuous time system is said to be linear time invariant if it satisfies all of the following. Firstly, consider two different inputs, x1 of t and x2 of t. Let's assume that our system, given x1 of t at its input, produces the signal y1 of t. And similarly, when given x2 of t at the input, it produces y2 of t. If the system is linear, then we are guaranteed that if we apply x1 of t plus x2 of t to its input, then we are guaranteed that the output is going to be y1 of t plus y2 of t. And furthermore, by linearity, if I apply a scalar times x of t to the input, where given x of t, I know I get y of t coming out. If I then apply 2 times x of t to the input, for example, then I'm guaranteed of getting 2 times y of t coming out. Linearity guarantees these two properties. Time invariance guarantees a different type of a property. If we know that if x of t goes into the system, we will get yt coming out, then we know that if xt minus a delay goes into the system, then we're going to get out the same y, just delayed by exactly the same amount. That's time invariance. The intuitive way of understanding time invariance is to say that whatever you put into the system today, and you get a certain output, you're going to get the same output if you put the same input in tomorrow. The input-output relationship does not depend on what day of the week it is. Now, why do we care about LTI systems, and what's the connection between LTI and frequency domain? Let's start with a general system. We want to try to understand its behavior. That means, for a given input, we want to be able to predict what its output's going to be. We can imagine that there are some inputs that are relatively simple to predict what the output is going to be, and there are going to be other inputs that are going to be very difficult for us to predict what the output's going to be. It depends on the system. So the first thing we should do is study the system with respect to these so-called simple inputs. Once we can understand what the system does with these simple inputs, then we can ask, well, how does the system work in response to a more complicated input? In general, this is very hard to answer, in fact maybe impossible. But with a linear time invariant system, if we know what the system does in response to a signal x1, and if we know what the system does in response to an input x of 2, then we already know what it does in response to the input x1 plus x2. And in fact, what it does to the input 5x1 minus 10x2. We have gone from knowing how the system behaves on a small number of inputs to knowing how the system works on a very large number of inputs. And if we're very lucky, maybe any input can be represented as a suitable linear combination of our input signals. The fact that the system is also time invariant really helps with this. We can take a simple signal and we can delay it or push it forwards into the future, and again we know exactly how the system is going to respond. So what we will see is that there are two very nice properties of LTI systems. If we put a sinusoid into an LTI system, we get out a sinusoid of the same frequency. This is what we mean by applying a simple signal, a signal that it's easy for us to understand what the output's going to be. If we put a square wave into a system, we are probably not going to get out a square wave. But if we put a sinusoid in, and it's an LTI system, we will get a sinusoid out of the same frequency. Very simple behavior. Because it's an LTI system, if we know what it does to sinusoids, then we know what it does to linear combinations of sinusoids, and we know what it does to delayed versions of linear combinations of sinusoids, and so forth. And it turns out that essentially any signal we care about can be represented by a sum of sinusoids. And that's why frequency and LTI systems go hand in hand. We can understand completely how an LTI system works if we understand what it does to each particular frequency. And moreover, the behavior of an LTI system in response to a sinusoid coming in is very easy to understand. We therefore get a complete picture of how LTI systems work by looking at them in the frequency domain. Let's consider the two types of linear time invariant systems. We can have a continuous time system here, where the input is x of t and the output's y of t. And we can have a discrete time system where the input's x of k and the output is y of k, where I use square brackets to denote discrete time. A fundamental property of a system is what's known as its impulse response. If you're on the side of a mountain and call out "Cooey," then what you hear back is, roughly speaking, the impulse response. Of course, to be more mathematically precise, your cooey would have to be infinitely short in time and infinitely large in amplitude. Indeed, for a continuous time system, the definition of an impulse is a Dirac delta function, which we think of as the limit of a sequence of rectangles that get narrower and taller in such a way that the area under them is always equal to 1. So if I choose x of t to be the Dirac impulse function, delta of t, then the output I get y of t is going to be the impulse response by definition, and we're going to denote that by h of t. Besides the cooey example, you can also think of the impulse response of a car's suspension system. If a car goes over a short sudden bump, then the resulting behaviour of the car is its impulse response. In discrete time, an impulse is a lot more realistic. It's simply given by the function whose output is a 1 if k is equal to 0 and a 0 otherwise. The impulse response of a discrete time system is the output when the input x of k is equal to delta of k, and we denote the impulse response by h of k. Of course, we can define the impulse response for any system, but if the system is not time invariant, then the impulse response today might be different from the impulse response tomorrow. In fact, if engineers have to deal with such systems, they're going to define a series of impulse responses depending on the time of day. But if the system is not even linear, that's not going to help much. You see, the advantage of being able to talk about linear time invariant systems is that if we know the impulse response, we actually know its output in response to any input. Now, a quick caveat, mathematically speaking, this is not entirely correct, but since in engineering we deal with real-world signals, we may as well just assume that everything is possible and use this more general language to make life easier and to allow us to get the intuitive understanding of what's going on. So let's start with a discrete time system, as it's a little bit easier to see what's happening. Why does the impulse response fully describe its behavior? Let's assume that my input sequence h of k is going to be all zeros from the infinite past, then 1, 2, 3, and then all zeros to the infinite future. And I need to mark on where time k equals to 0 is, which I'll do like this. So that means at time k equals to -1, the inputs are 1. At time k equals to 0, the inputs are 2. And at time k equals to 1, the input is a 3. If we know the impulse response h of k, we should be able to work out what is the output of my discrete time system. Well, because of the linear time invariant nature, I can decompose the problem. First, what is the output going to be if the input was just this 2 here, times 0? Well, by linearity, we know that the output is just going to be twice the impulse response. Remember, the impulse response is the output if we put in a delta function, and here we're just putting in twice the delta function if we pretend the 1 and the 3 are 0. So in response to a 2, if 2 goes into the system, we're going to get out its impulse response. So h -1, h0, h1, etc. will be my output. Of course, I need to scale it by the factor of 2, so I add a 2 in front of the terms here. For the 1, if I put a 1 into my system, well, ordinarily I would get out just the impulse response if that 1 had occurred at time k equals to 0, but it's been shifted 1 unit to the left. So therefore my output, and I'm going to assume that my time 0 lines up with this line here, k equals to 0. If I apply a 1 to the input at time k equals to -1, then I'm going to get my impulse response, but shifted to the left 1 unit. So I'm going to get h0, h1, h2, ... Similarly for my 3, I need to make use of both linearity and time invariance. In terms of the time shift, my impulse response is going to be delayed by 1 unit. I'm going to get out h -2, h -2, h -1, h0, h1, ... That's due to the 3 arriving at time k equals to 1. And then it's got a strength of 3, so I multiply everything by a 3 here. And then my final output, my actual output, is given by just adding these up. That's the linearity of the channel. So in particular, at time 0, my output is going to be h1 plus 2h0 plus 3h -1. My output at time 1 is going to be h0 plus 2h1 plus 3h0, and so forth. The reason I wrote it that way was to try to show you intuitively what's happening. That's good for understanding, not so good for mathematical manipulation. To do the same thing mathematically, it would look like the following. I start off with my signal x of k. As we saw down here, we can treat any signal as a sum of delta functions just shifted in time and scaled in magnitude. Given any x of k, I can decompose it as an infinite sum of k prime equals -infinity to infinity of my x at k prime. This is going to serve as the coefficient I have in front of my terms here, times my delta function, k minus k prime. So you see, if k prime equals to 0, this means that I'm going to have my delta function here firing at time 0, and it will have magnitude at x of 0. If k prime is equal to 1, my delta function here is going to fire at time k equals to 1 with a magnitude of x of 1. So this expression here just gives me my input sequence as an infinite sum of delta functions. Because I know the response of my system to any individual delta function, and because my system is linear and time invariant, I therefore know what its output's going to be. Precisely, I know that y of k is going to be equal to, because the system is linear, the sum comes outside the front. Again, because the system's linear, this scalar comes out the front. And then I'm just left with my delta function going into the system. It's been shifted in time by k prime, but because my system is time invariant, I know its output is going to just be the impulse response shifted by the same amount in time. And that's it. This is the complete characterization of the behavior of a linear time invariant system. This is not true for a general system. In order to be able to write this, I had to make use of the fact that the system was both linear and time invariant. This is what's known as a convolution, and we can say that the output y is the convolution of the input x with the channel impulse response h. By a simple change of variable, we can show that convolution is commutative, which means that this is the same as the sum of k prime, goes from negative infinity to infinity, of h of k prime, x of k minus k prime, which sometimes people prefer to write, even though the two are equivalent. For our continuous time system, exactly the same thing is true for exactly the same reason. And we get that if we know the impulse response h of t of a continuous time system, and if the system is linear and time invariant, then y of t is given by the convolution of the impulse response with the input to the channel. This is convolution in continuous time, and this is convolution in discrete time. They are essentially one and the same thing. It's important to have an intuitive understanding of what convolution means. It might look complicated, but it's not. It's a linear operator, which makes it simpler, but more importantly, we can intuitively understand convolution as a type of smoothing. For example, if my input were a sudden transition like this, and if my impulse response were a smooth Gaussian, then intuitively I would expect that my output to be a smooth version of the input. Now, of course, this won't be exact, but the point is convolution serves as smoothing. Now, why can I confidently claim that? Well, let's have a look again at the formula. The output is the input of the channel impulse response convolved with the input. And this is just a summation. If this h term were not here, then I'm just forming the average of my x values. Having this h term out the front now just means I'm forming a weighted average of x. When I form a weighted average of something, I am averaging it out. I am smoothing it out. And so we can think of convolution as smoothing functions. This interpretation is very interesting because let's think of a practical problem. The sound waves from my mouth are going into the microphone. Before they get there, they might bounce off the ceiling and the side walls, etc. So there might be a direct path and several indirect paths, which means that the microphone is not receiving an exact replica of what I'm saying. We can model this by a linear time invariant system. If I were to do cooey really loud and sharp and listen to the echo, I could figure out the impulse response of this room. Mathematically, the sound waves coming out of my mouth are convolved with this impulse response. They are being smoothed by it. If I want to, for some bizarre reason, be able to recreate my voice perfectly, I'd have to get my computer to undo this smoothing operation, reverse this convolution process. But intuitively, if something's been smoothed, it's hard to unsmooth. It's like you put sugar in your drink, stir it up, good luck getting the sugar out. And so I expect to see mathematically the same thing. Even if in theory it might be possible to undo the smoothing, in practice we'll find it's going to amplify noise. We could try to obtain the original signal perfectly but have lots of noise. We could try to do nothing and have the least amount of noise, or we could seek a compromise somewhere where we try to get back to the original signal but still not have as much noise as if we were to recover it perfectly. Put simply, a basic question to keep in mind is if a signal gets corrupted by going through some sort of a system, how can we equalize it? How can we recover the original signal? Let's see how we can solve such problems by working in the frequency domain. I have an input x of t. It goes through a linear time invariant channel, which means that the channel is characterized by its impulse response h of t. The output y is the input convolved with the channel impulse response. We know convolution is a type of smoothing, but that doesn't help us invert this problem. Given y, how can we recover x? In statistics, people use different ways of graphing the same data because different graphs give us different ways of viewing the information. Some graphs reveal one piece of information more readily than another graph does. In the same way, we are going to transform our problem. We are not changing the problem in any way. There's a one-to-one mapping. It's what's known as the Fourier Transform, which we'll study later. It takes an input signal x of t and produces its frequency content, another function that summarizes what frequency components are in x. We can do the same to the output, take its Fourier transform to find its frequency content. And it turns out we can do the same thing with h, the channel impulse response. And moreover, we have a relationship between these three variables. It turns out that the output y is going to be equal to the product of the input x times the channel impulse response h in the frequency domain. If we accept that the transformed version of my output is equal to the transformed version of the impulse response multiplied by the transformed version of the input, then we can easily solve our channel equalization problem, at least in theory. While convolution is a bit difficult for us to understand, we can only think of it in terms of smoothing, multiplication is something we have grown up with. We understand multiplication well, and we know that to invert multiplication, we do a division. So in theory, I get that my original signal must have been the output divided by the transformed version of the impulse response. Note that in the frequency domain, the channel behavior separates. In the time domain, the output at y of t can depend on all of x of t. If the impulse response h is doubly infinite, if it's infinite in both directions, then the output now depends on both the past and future inputs. It can be quite complicated. Whereas in the frequency domain, we see that the output content at a certain frequency is simply equal to the input content at that frequency multiplied by the impulse response at that frequency. The output at one frequency does not depend on the input at any other frequency, nor does it depend on the channel impulse response at any other frequency. Tangentially, note that if I have an input that goes through two systems, h of 1 and h of 2, to get y of t, in the frequency domain, I can then write capital X goes through capital H1, goes through capital H2 to y. People understand what this means. And these systems simplify to x of t goes into, this one would be h1 convolved with h2 to give me y, and this one would simply be h1 times h of 2 to give me y. Because convolution and multiplication are commutative, I can combine these diagrams like this, and the order doesn't actually matter. A block diagram representation of our room equalization problem is therefore the following. The input from our microphone goes through our room H, and then our equalizer simply applies the reciprocal 1 on H to cancel out the effect of the room, and because H times 1 on H gives me 1, I get that the output is the same as the input. We mentioned before that convolution means smoothing, and undoing smoothing should be difficult. So how do we see this in this representation here? Well, if my room absorbs certain sounds, that is, if I get deconstructive interference, that means that at some frequencies, h of omega is going to be close to 0. And 1 on 0 is certainly not defined. So if my room perfectly absorbed a particular frequency, meaning if I transmitted a 1 kHz signal in my room, I won't actually hear anything. This of course depends on where the sound comes from and where I'm listening from, etc. But if I get perfect cancellation at a frequency, then I'm not able to recover the frequency content of x at that frequency. If I have severe attenuation, then the only way to try to recover those frequencies is to multiply them by a very large number. If, for example, h at a certain frequency is 1 on 1000, then I must multiply my amplitude at that frequency by 1000. This means that I'm actually going to be amplifying noise in that frequency band, and hence we're not actually going to be wanting to do this in practice. We can see already how working in the frequency domain gives us a lot more insight than working in the time domain with convolutions. Nothing magical is happening, it's just like moving to a different type of a graph to represent your data, and suddenly some features become more obvious in that graph compared with other ways of graphing the data. Let's now look at why we can claim that x at omega represents the frequency content of x of t at the particular frequency omega. First, remember e to the j omega naught t is equal to cos omega naught t plus j sine omega naught t. While humans are used to sinusoids, it's a lot easier mathematically to work with these complex exponentials, which often I will refer to as a sinusoid for convenience. And this is the reason why we can justify doing it. Our ordinary sinusoids, real-valued ones, can actually be written in terms of e to the j omega naught t and e to the minus j omega naught t. If you expand this one as well, then you can, by adding or subtracting the two, isolate the cos or the sine term. You can also, by multiplying by a complex number out the front, get a cos with any phase shift you like, as well as any magnitude you want. If I have my LTI system here with impulse response h, remember before we said to understand a system, I want to put some sort of a simple input into it and then try to see what behavior I get at the output. Well, it turns out that the simple input to put in is a sinusoid. Remember, I'm going to use the term sinusoid when referring to complex exponential sinusoids. It turns out if I put a sinusoid in at frequency omega naught, then the output is always going to be of the form some complex scaling factor times a sinusoid of exactly the same frequency. You can show this is true by taking the convolution equation and substituting in a complex exponential sinusoid and seeing that you get out another complex exponential sinusoid, just possibly with a phase and magnitude shift, determined of course by the channel impulse response. This coefficient a here depends on the frequency omega naught, and so we're going to call it h of omega naught in this example here. We will see presently that my h here really is the Fourier transform of the channel impulse response. To emphasize what's happening, imagine now I put in a signal e to the j omega naught t plus e to the j omega 1 t, and I can even change the coefficient out the front, so I can have alpha 0, alpha 1 here, and these can be complex numbers. If this signal goes into my system, then the output is going to be, well, because it's linear, I can process these input signals, these subcomponents separately, so the output is going to be alpha naught, h of omega naught, e to the j omega naught t, that's this component here, plus, and now I first process this component, and then I just multiply it by alpha 1 due to linearity, and so my output is going to be given by this. You might ask about translation invariance, and sinusoids are very special in that regard. If I were to delay a sinusoid, then I can bring this factor out the front to get e to the minus j omega naught d times my sinusoid, and this is just a complex number, and so delaying a sinusoid is the same as just changing its phase by multiplying it by a complex number out the front. Therefore, in my decomposition here, I can take any signal I like, x of t, and try to write it as a linear combination of sinusoids. If I can do this, then I can predict the output of my channel or of my system here. The key point is that all the Fourier transform is doing is computing this decomposition here. Let's have a look why. In the first instance, it's not the Fourier transform we care about, it's its inverse Fourier transform. This gives us a representation of a signal x of t as a sum of exponentials. The integral here is just an infinite sum, and we can have a look at this term in here and compare it to what we did up here, and intuitively we see that in here, if omega is equal to omega naught, I get my x of omega naught times e to the j omega naught t, and when my omega is equal to omega 1, I get my x of omega 1 e to the j omega 1 t, and so forth. And if we compare this with what we did earlier, we see that this is just my alpha naught, and this is just my alpha 1. So the inverse Fourier transform representation of a signal is exactly what we want in order to figure out how a channel acts on this input signal here. We have decomposed our input x of t into a sum of complex exponentials. We know how a channel is going to behave on a complex exponential, and due to linearity, we can therefore deduce that the output is going to be given by the same type of a sum. Here's the output up here, and all I did was modify each of the coefficients by multiplying it by this capital H. In other words, I expect my output y of t is going to be equal to the same type of a sum of the coefficient at a certain frequency coming in multiplied by the impulse response at that frequency. Then I get the sinusoid at that same frequency. So here, a sinusoid at a certain frequency comes in. The output is going to be a sinusoid at the same frequency, just modified by the channel impulse response at that frequency. And that's how we intuitively understand this formula here, which is saying nothing more than the output in the time domain is equal to the product of the input x and the channel impulse response h. Here we are saying that the output y of t can be represented by a sum of sinusoids, each with a magnitude of x of omega times h of omega. That's why we say that the output at the frequency omega is given by x times h, because this is the magnitude of the amount of this sinusoid that's present in the output signal. Let's summarize what we have said. If e to the j omega naught t goes into a linear time invariant system, what we get out is the same e to the j omega naught t multiplied by a complex number, which depends only on the frequency omega naught. This is due entirely to the channel being an LTI system. As a consequence of the channel being linear time invariant, we get that if I have a sum of complex exponentials going into the system, the output is another sum of the same complex exponentials going in, just with their magnitudes modified by the same factor we observed in the first case here. Nothing changes when we go from a finite summation to an infinite summation. If I have an infinite number of sinusoids going into my system, then the output is going to be an infinite sum of sinusoids of the same frequencies, with each one modified by the channel impulse response. My channel impulse response is defined right here. under this first property, and everything else is a consequence. This follows, and this follows directly from this very first property here and the linear nature of the channel. Looking at the formula for the Fourier transform and its inverse, we see that this last consequence here is simply saying that the inverse Fourier transform of x of omega gets mapped to the inverse Fourier transform of h of omega times x of omega. The inverse Fourier transform is invertible. Indeed, its inverse is given by the Fourier transform, which we'll look at next. So given any signal x of t, I can take its Fourier transform to get big X of omega. And similarly, I can call this term here y of t, the channel output, and I know that the Fourier transform of y of t has to be h times x. In other words, the Fourier transform of my output y is going to be my h of omega times the Fourier transform of my input x of t. Remember, we just started with this one condition here that is true of all linear time invariant systems, and we have derived everything else on this page. It's a consequence of this first fact up here. For a given system, we know how to find h of omega. We simply put in a sinusoid of a particular frequency, look at what we get out, and then we define h of omega to be the magnitude and phase change of that sinusoid going in. We have almost derived our earlier diagram, which showed that to understand how an LTI system works, we can either look at it in the time domain with a convolution or in the frequency domain with a multiplication. The only thing we haven't done is shown that this h of omega term here is also a Fourier transform of something interesting, and indeed it's the Fourier transform of the channel impulse response h itself. To show the connection, we just need to start and look at the definition of the channel impulse response. By definition, the impulse response is what we get out of our channel when we put in a direct delta function into the channel. If we are interested in what the Fourier transform of the channel impulse response is, then we first start with a Fourier representation of a direct delta function. We ask the question, can we represent a delta function in this summation form here as an infinite sum of complex exponentials? It turns out that yes, we can do it, and in fact the Fourier transform of the delta function is just the constant function 1. And this is important to understand intuitively. It says that if we put an impulse into a system, we are exciting every frequency component by the same amount. This is made up of a sum of sinusoids. In fact, it's a sum of every single possible sinusoid, each sinusoid having a magnitude of 1. We uniformly excite all modes of the system. This is why putting in the delta function is a good way of understanding the channel behavior. If we had forgotten to include some frequency components, then we would never know how the system responded to inputs at those frequencies, and therefore we couldn't work out how the system responded to arbitrary inputs. Any input that contained a frequency which we had not yet probed, we could not determine what the output would be. We know from before that the inverse Fourier transform of x of omega gets mapped to the inverse Fourier transform of the input x of omega in the frequency domain multiplied by the frequency response of the channel, h of omega. In our case, we are putting in a delta function on the left, and we're getting out the impulse response, h of t, on the right. This means that h of t is equal to the inverse Fourier transform of h of omega times x of omega. But we've seen over here that x of omega is just equal to 1. Therefore, we get that h of t is the inverse Fourier transform of our big H of omega, exactly as claimed. We can take the inverse of this and get that h of omega is the Fourier transform of the channel impulse response, h of t. If you don't like this derivation of how we find that the Fourier transform of the channel impulse response gives us our frequency domain response, we can go in the reverse direction, which we'll look at now. We have, for a linear time invariant system, that if we take the Fourier transform of the input, take the Fourier transform of the output, then there's this relationship the output y of omega is equal to h of omega times x of omega, and the only question is, what is this guy here? We have one answer, we know how to find it. Remember, I put in e to the j omega naught t in, and I look at what I get out. What I get out is going to be some scalar, a complex scalar, times e to the j omega naught t, and whatever this scalar is, I define to be h omega naught. So this term in here, we know how to find it. The only question is, what is its inverse Fourier transform? Why might we care? Well, h of omega is so special, it seems natural to ask, what is its inverse Fourier transform? Here's our question. What is the inverse Fourier transform of h of omega? Remember, we have a system, we can play with what we put into the system, and we can observe what we get out of the system. So what can we put into the system to make us work out what h of omega is? It seems natural by looking at this equation, the simplest thing to do is to set x of omega to be equal to 1, because then my output y of omega is going to be just h of omega. And of course our system operates in the time domain, so that means that my output, what I'm going to observe, is actually y of t. So if I can find an input x of t whose Fourier transform is equal to 1, then my output y of t is going to be the inverse Fourier transform of h of omega. While there are some mathematical intricacies which I am ignoring, if we just go to a table of Fourier transform, inverse Fourier transform pairs, we can find out exactly what we need x of t to be if we want its Fourier transform to be 1. Looking up in tables, we see that we need x of t to be the Dirac impulse response. And this is the proof in the other direction that the Fourier transform of the impulse response of the channel is h of omega. Just a reminder of what the Fourier transform is mathematically. First, we start with the inverse Fourier transform representation of a signal x of t. This is the more important one. So what we want to be able to say is that any signal x of t can be decomposed as a sum of sinusoids. Why? Because sinusoids are simple signals to put into an LTI system. We can understand the behavior of the system by understanding it with respect to what they do to sinusoids. So our inverse Fourier transform representation is what we care about, and it says we can decompose our signal into an infinite sum of these complex exponentials. The Fourier transform is simply the inverse of this operation. Given an x of t, we want to find these coefficients here so that we can make use of this representation. That's all the Fourier transform is doing. It's giving us a means of finding these coefficients here, which is all we really care about. And it turns out that the expression for the Fourier transform is very similar to the expression for the inverse Fourier transform. And the consequence of this is that we essentially have some sort of a duality going on, where results in the time domain have got analogues in the frequency domain, due to the fact that these formulae are so similar to each other. Here's the explicit formula for the Fourier transform, and to emphasize, its use is that it gives us these coefficients here that we can substitute into this inverse Fourier transform representation of an arbitrary signal x of t. Closing the loop, we return to our original diagram. We have our continuous time system that we care about. We can take the Fourier transform of the input, the Fourier transform of the channel impulse response, and the Fourier transform of the output, and we get an equivalent representation of our system in the frequency domain. In the time domain, the output y of t is going to be the convolution of the input with the channel impulse response, which we normally write round this way round. In the frequency domain, the output y of omega is going to be equal to h of omega times x of omega. This transformation is predicated on the fact that we care about complex exponential sinusoids. They are the simplest signals to consider. So if my input here is e to the j omega naught t, the Fourier transform of that can be shown to be 2 pi times a Dirac delta function located precisely at omega naught. In the frequency domain, we draw it by simply putting a little up arrow at omega naught. You might ask, why isn't the Fourier transform of e to the j omega naught t just equal to the function that takes the value 1 at omega naught? Well, the problem is that in this representation here of our signal, an integral is essentially blind to what happens at an individual point. If x of omega is equal to 0 everywhere, but is equal to the finite value 1 at a single point, this integral will still be 0. The only way to have a significant difference in this integral representation is to put in something with an infinite magnitude in here. Of course, to deal with this mathematically requires going through some hurdles, but as engineers we can just safely ignore all of this and work with direct delta functions. Importantly, we can check that this really is the Fourier transform simply by substituting it into this equation here. Remember, the purpose of our direct delta function is when we integrate it, it pulls out just a single term. So if we substitute this into here, it's going to pull out the single term e to the j omega naught t. And the factor 2 pi out the front is to offset the factor 1 on 2 pi out the front here. Returning to our diagram, if the input in the frequency domain is a delta function, then the output y in the frequency domain is going to be exactly the same delta function, just with its magnitude altered. So the output here is going to be 2 pi h at omega naught delta omega minus omega naught. And then the final output of my channel y of t is just the inverse Fourier transform of this expression here. As we said just before, it's very easy to evaluate the inverse Fourier transform of a direct delta function. It simply pulls out individual terms here. And so we find that our output y is actually h omega naught e to the j omega naught t, agreeing with how we defined h of omega in the beginning. If the input is e to the j omega naught t, the output is e to the j omega naught t with its magnitude and phase altered by h omega naught. Everything fits together as it ought.